Continuing on with the substitution reactions, this is a very critical part of learning about substitution reactions. So in the previous presentation, I introduced you to SN1, SN2 reactions, but I didn't go too much in detail. Now we are going to go a little bit more in detail about what are the factors that affect substitution reactions. So first of all, what are the factors? Here are the four factors. For SN1, SN2, we're going to do both of them at the same time so you can see the similarities and the differences between the two. Okay, so first of all, the substrate is the most important thing for any kind of a reaction. So in the previous presentation, you might have heard me saying, well, you have a tertiary substrate and whatnot, and like how did she say that? How did she know that? Well, now you're going to learn that. That's why I said the last presentation was not a complete presentation. Okay, so anyhow, substrate is very important for us. The strength of the nucleophile, the nature of nucleophile is really important for us. The leaving group is important also because remember I said both of these are negatively charged. So why is it that the nucleophile can get rid of the leaving group, okay, in there? And the last thing we will talk about is solvent. Now we haven't even mentioned solvent until now. So, it's like, what does that have to do with it? We'll talk about that. So these three things are the most important for us. Solvent, I would say, is the most important when you're actually practically doing the reaction, okay? Then it's kind of becomes important, like how do you do it in the lab? Okay, all right, so let's get started. So nature of the substrate first. Okay, so remember what the mechanisms are. Two mechanisms, SN2 and SN1 mechanism. So for the first one, SN2, in the mechanism, this is a backside attack, right? It's a backside attack, which means that the carbon that is getting attacked needs to be more accessible. Okay, so the word steric hindrance should come to your mind, okay, all the time here. So the carbon should be accessible. In the SN1 reaction, it's a carbocation formation, so the carbocation must be stable. Now, how sterically hindered the carbon is, that's not important, okay, because here the nucleophile is not attacking from the backside. In SN2 it is. So here it is important for the carbon to be accessible. Here in SN1, once the carbocation is formed, it is already accessible from both sides, from two sides, not even just one, from two sides it's accessible. So the formation of the carbocation, that's the important thing. The carbocation must be stable, right? So this next thing that I want to mention here is then the steric hindrance. Okay, so steric hindrance in SN2 becomes really important because if the carbon that needs to be, reacting with the nucleophile, if that is not accessible, how is the reaction going to occur? It's not going to, okay? So here crowding is not an issue, as I said, okay, because the trigonal planar shape is there, so we don't have to worry about steric hindrance in SN1, okay? For most part, we don't have to. So how does it work, okay, as far as what kind of carbons we need, okay, for SN2 versus SN1? So in the case of SN2 reactions, if you have something like a small substrate like this, which is just a methyl with a leaving group, this is going to be the best reactant ever because the hydrogens are so small of atoms that they will not cause any kind of steric hindrance, okay? So this is the most reactive. Then the primary halides or primary carbons are going to be more reactive. Now remember, when we're talking about carbon, we're talking about the electrophilic center, okay, where the leaving group is. So primary leaving group, secondary leaving group, tertiary. Tertiary is the least favorable for SN2. It's the opposite for SN1. Now SN1 here is a new thing also, okay, this is called an allyl cation, but it doesn't have to be an allyl cation of just 3 carbons. It can be 7-8 carbon structure with a double bond and the carbocation in this kind of a attachment. Okay, so we'll talk about that when we talk about it in just a few minutes. This is going to be most favorable, followed by tertiary, secondary, and then primary. And see, this is the methyl with the leaving group is the least stable, okay, of all. So this is kind of how it works. Now, when we do all of these things, okay, you will have to keep all those conditions in mind that we have studied for SN1 and SN2, which means that, you know, the steric hindrance, the the structure of the carbocation, and so on and so forth. Here I've just mentioned a little bit to you about the stability versus reactivity. If something is more stable, it is not going to be as reactive, okay? So, you know, when the carbocation is more stable in SN1, you know, that's kind of what you need for an SN1 reaction, all right? So SN2s are not going to work by carbocation mechanism. Now, one other thing I want to mention here before I move on is, you know, when we talk about all of these things with the substrate, nucleophile, leaving group, and all that, there are always going to be exceptions, okay? Which is why it makes this chapter a little bit more challenging than others, because there's nothing written in stone. There are going to be very few things that work absolutely perfectly SN1, SN2, okay? But there are going to be so many things where you have to decide, okay? So don't take anything and memorize it. Learn the concepts, learn the explanations that I'm giving you, and try to understand them, and then you decide, okay, from there, how you're going to proceed with the reaction. So nature of the substrate, let's go ahead and talk about the stability of carbocation just a little bit. So here I've given you multiple substrates, and then I've given you the carbocations that are going to form from all of these. Okay, so if you have a substrate like this, okay, where you have a double bond and the leaving group on the third carbon from the double bond, that's the most important thing here. Okay, so 1, 2, 3, and this kind of an attachment is the allele. That's what I was talking about. So, all right, here I've written it also. Anyway, so that's the allele. Okay, you have seen the tertiary before, okay, because we've learned about primary, secondary, and tertiary classification. So here is the tertiary, secondary, and then primary, and then we have the methyl cation. Okay, so I've given you all of these so you can see what they look like and what the substrate looks like, you know, if you have primary versus allele, okay, in there. So now we've talked about the stability, that for SN1 you need more of this kind, for SN2 you need more of this kind. Okay, that's kind of what we're talking about, and you can write these things if you want to, although I think I've given it to you in some places, but you know, you can write that out. So the stability of the carbocation, why it is more stable. First, let me talk about the allele, because that's what I've given you over here. So let's talk about that. And what happens in the allele cation is that you end up getting resonance. Remember, this is the resonance arrow. So you end up getting resonance, and because of that, there is delocalization. Okay, here is the hybrid, okay, for that. And remember, we've drawn hybrid in one different way before, and that was like this. Okay, so this one I gave you as in the electrons are spread all over here. So that hybrid with the delocalization of electrons is what makes the allele cation more stable even than a tertiary carbocation. Okay, now that's the resonance part, okay, where we learned about delocalization before. Now let's talk about why the tertiary is more stable than secondary than primary, right? This is the most stable one. So the reason that a tertiary cation is more stable than secondary versus primary has to do with all these groups that are around the cation. All of these groups are electron dense groups, which means they have the CH3s, right? So there could be CH3 here, or it could be any other group, but they're carbons and hydrogens. So the more carbon and hydrogens you have around these carbocation, the more stabilizing factor it will be on the carbocation, because there are electron densities which are negative, right? And they're just supporting it. Now, it doesn't diminish anything about the positivity of the carbocation. It's just that it is more stabilized. Okay, so for example, you know, if you have a checking account and you also have a savings account, so if your checking account runs out of money, your bank can always take money from the savings account, put in the checking. That's kind of what we're talking about. So this is a savings account, and then here is your checking account. All right. In the secondary carbocation, you can see that you have less electron density. Don't forget, here, the third bond is hydrogen, okay? And in this primary carbocation, there are 2 hydrogens here. So the 2 hydrogens don't really contribute that much to electron density because there's only 1 CH3 that is contributing. So 3 CH3 versus 2 CH3 versus 1, versus nil, you can see that the stability of the carbocation is decreasing because, yeah, if you want to think in terms of savings accounts, now you have less and less of that electron density there. Okay, so that's the nature of the substrate and why the stability of carbocation is important. Again, SN1, more of the allyl and the tertiary, and then SN2 is more of the methyl cation. Now for the steric hindrance for the nature of substrate. Okay, so the steric hindrance means that your carbon should be accessible. So if the carbon is not that accessible, like in this case, then the nucleophile cannot reach this carbon center, this electrophile. So what I've shown you here with this and the space-filled models, and these are the space-filled models, and I know kind of look awkward, but that's really what atoms look like in reality. So here in the space-filled models, you can see here is the chlorine. The green one is the chlorine. So the chlorine is kind of getting overcrowded by all the methyl groups, okay, around it. So which means that that carbon where the chlorine is attached, that carbon is not so easily accessible anymore, all right? So for an SN2 reaction, you want the carbon to be accessible. So this is the best substrate for SN2. So primary better than secondary, better than tertiary. In tertiary, the carbon is not even accessible. Okay, so I mean tertiary wins out even for SN1 regarding steric hindrance and also stability of the carbocation. Okay. So here are some solved problems, okay, for the nature of substrate, because you have to be able to look at the substrate and then be able to predict what kind of reaction it will be able to do, whether SN1 or SN2, okay? So classify the substrates as primary, second, tertiary, predict the mechanisms of the reaction. And we're not talking about nucleophile, like what kind of nucleophile, we're not mentioning that at all. So here is just a matter of predicting what do you think it might be, okay, for the SN1 or SN2 reaction. So here you have 1-chlorobutane. You should be able to write the structure for all the nomenclature. And so write the structure, okay? Don't assume anything, okay? Go ahead and write the structure so you can clearly see whether this is primary, secondary, or tertiary. And in this case, this is primary substrate should undergo SN2, okay? A lot more. I've given you a little bit more explanation over here just for your sake. I'm not going to read it all the time, but just so that you have it for your record, okay? That why a primary substrate is good for SN2. In B, I can see a double bond, so I count my 1, 2, 3, and then 1, 2, 3. Here is the bromine, and so which means that when this leaves, I will end up getting an allylic cation because this is an allylic halide, and so therefore it should give me SN1 reaction. Okay. Now, as I said before, okay, allylic is 1, 2, 3. All right, which means that if this was this kind of a halide, you have to include the double bond when you're counting, okay? So 1, 2, 3, 4. In this case, you don't have any kind of allylic halide, all right? Or you don't have that kind of a carbocation formation that will give you resonance, okay? So then in this case, your bromide is just a primary bromide. That's it, okay? There is nothing else. There's no allylic thing. The allylic thing has to come from the 1, 2, 3 kind of a system, okay? So here, even if you get rid of the bromide and you say, okay, I just want to write it out. So here I'll write it out for you. So here, once this bromine is gone, then you end up getting a positive on this carbon, right there. So you cannot draw any more resonance, okay? What kind of structure will you draw? Because there is nowhere for the double bond to move to involve the carbocation, okay, in resonance, because that's the most important thing for allyl cation, is to involve the cation in the resonance, which is not happening. So this is a traditional primary halide. Okay, so the location of the double bond is the important part here. Okay, so this one is easy enough, right? This is tertiary halide, so tertiary means SN1. 3-bromopentane, now when you have a secondary halide, then it's always going to be a problem, okay? Because the secondary halides can do either SN1 or SN2, depending on, the nucleophile also, okay? So it's not just dependent, again, on the substrate anymore, because you can have a lot of steric hindrance, okay, over here. Now, if you have this kind of a halide, which is also secondary, but look at this, you have a methyl and an ethyl, but in this case, you have two ethyl groups. Two ethyl groups meaning that it is more crowded, right? So it's quite crowded, which means that secondary, this might actually undergo more of SN1 than SN2. Okay, this is what I would predict. Right here, I just wrote either SN1 or SN2, but I think because of steric hindrance, this is going to be a little bit more SN1, and the rest of it depends on the nucleophile, okay, which we still have to talk about. So, that's kind of my thinking on here. Let's look at the nucleophilic strength now. Now remember what we said before is that the nucleophile and the leaving group are both negatives, or even if they are neutral, they're both electron rich. Okay, so why is it that the nucleophile is able to get rid of the leaving group on the substrate? So that has to do with the strength of the nucleophile. It is stronger than the leaving group, but stronger in what? Stronger in negative charge. Okay, since both of them are negatively charged, the nucleophile is stronger in negative charge, or it is richer in electron density than the leaving group is. Okay, so the best way to look at a nucleophile is generally as a base also. Okay, that will help you. So we've done acids and bases before, and I explained a lot of detail to you about, what it means to have a strong acid. You can go back and, listen to that again if you want to. So I didn't go over so much about bases because, as I said to you, is that, bases are completely opposites of acids. So once you know your acid and you know what the conjugate base is, so then you can figure out the strength of the base, because a strong acid gives you a weak conjugate base and a weak acid gives you strong conjugate base. Okay, so keeping that in mind, let's talk about the nucleophile and the strong base. Okay, how are they related? So number one, they're related because they're both negatives. Okay, because bases are also going to be negatives, although there are some bases like water that is neutral. Okay, and ammonia is neutral. So they can be neutral also, but they're generally electron rich. The main difference between a nucleophile and a base is that a base actually goes for a proton. Okay, both bases are characterized by their ability to abstract a proton, because bases react with acids, right, to get protons. Nucleophiles don't really care about protons. Okay, so which means a nucleophile actually goes for the electrophile. That is how you know a nucleophile is a nucleophile. Now, the nucleophile happens to be a base, so be it, but if you have a base, okay, that base will prefer to go for a proton. Okay, so let me give you an example over here for a base versus acid, or an electrophile. So let's say you have hydroxide, which, we've been talking about as a nucleophile. You treat that with HCl. You're like, yeah, I know this one. This one should be a typical acid-base reaction, right? Giving you water and the chloride. So again, you can view the chloride as a leaving group, okay, over here. And the product will be H2O and then Cl minus. Now, you can also have hydroxide with CH3Cl. Okay, so instead of having the H, now you have CH3. So once you have that, now the OH is going to attack the carbon, chloride leaves, and then you have the product. Now, what happened here is that the hydroxide actually went to carbon. It did not pick up any of these protons, okay, because these protons are not that acidic, okay. Why they're not that acidic? Remember, again, you need to have a polar bond. So the CCl bond is more polar than a CCH bond. Okay, so you have to be careful. So the hydroxide can be used as a nucleophile. It can also be used as a base, depending on what you're reacting it with. Okay, so here we're going to focus more, of course, of hydroxide as a base. If I ask you whether this is a base or a nucleophile, I have to give you a little bit of an idea of the substrate also, okay, for you to answer that question. So right now, that's not the question. Right now, the question is, how do you know it's a strong nucleophile? Okay, that's the more important question. So you can very easily say, if you know your bases, okay, that if you have a strong base, then that's going to be a good nucleophile also. Okay, so this is kind of a review of what we did in acids and bases, but definitely go back and listen to that lecture again if you want to, on how to determine acid strength. Okay, so first of all, charge. Okay, generally if you have something negative versus neutral, the negative is going to be more nucleophilic than the neutral one, because negatives are even more electron rich, okay, than a neutral would be. So that is a very simple kind of a comparison. The next one is electronegativity. Generally what's going to happen is something that is more electronegative will not be a good nucleophile. Okay, so anything on the left hand side of the periodic table will be more of a good nucleophile than anything that's on the right hand side. So nitrogen versus water, like in ammonia versus water. Now remember, nitrogen has electrons, oxygen has electrons, both are neutral. So how do you decide which one is a better nucleophile? You look at the electronegativity. Nitrogen is less electronegative. Okay, so if you look at the periodic table, whatever is on the left is going to be a better nucleophile. So hydroxide also, okay, better nucleophile than fluoride is going to be. Then the size of the anion or the atom. Atom would be, of course, if something is neutral. Anion would be if something is charged and negative. So generally what happens is the anion is going to be larger than the corresponding atom. So for example, I minus is larger than I. I does not even exist anyway. I exist as I2, as a diatomic molecule. But in any case, just kind of a, little throwing that out there for you. So the bigger the size of the anion, the better it is as a nucleophile, because it is more electron rich. Okay, so all you're looking for here is that it is more electron rich and therefore it is more nucleophilic. Okay, that's all it is. So you can see I didn't even add fluoride here because fluoride is not even a good nucleophile. Okay, here also you can see it's not a good nucleophile, and even according to size, it's not a good nucleophile. So you will see very few reactions of fluoride as a nucleophile, okay, because they're just not good nucleophiles. Okay, hopefully you're understanding the trend here. Okay, it has to do with electrons. Something that is more negative, something that is less electronegative, something that is bigger in size with more electrons, and then the last one here is with more electron density, okay, and inductive effect. So inductive effect we've talked about before also, okay, so let's just go ahead and review that anyway. So anything that has more electron density means that something is more electron rich. If it's more electron rich, it's a good nucleophile. Okay, it's as simple as that. So when you're comparing something like ETO minus to MEO minus, which ethyl group and methyl group is going to be a better nucleophile because it has more electron density. Now, this one also has to do with inductive effect. Okay, and remember what was inductive effect? We have talked about inductive effect as when you are sharing electrons, it's not like it's giving electrons. Okay, so when we talk about electronegativity, we'll talk about pulling electrons in a covalent bond. Inductive effect is kind of the same thing. Okay, so let me write the structures here for ethoxide. So CH3, CH2, O minus, and then CH3, O minus. So the O minus is the same, right? So all you're seeing here is a difference in number of carbons for both of these. Okay, so in the case of ethoxide, where you have 2 carbons, now more electrons are able to go towards oxygen to make it more electron rich. In the methoxide, you only have that 1 carbon that is supporting the oxide. Okay, so like if I'm going to fight, or if I'm going for a business deal or whatever, how much do I have support, financial support behind me, or people strength behind me, that kind of a thing. So this is the amount of strength that a larger group will give okay, to a negative. So the more carbons you have, the better it is going to be for the nucleophile. Okay, it's supported a lot more. So this can be with the number of carbons, or it can be with size also. Okay, so the sulfur size is much larger than oxygen. So a thio group here, SH minus, is going to be a better nucleophile than a hydroxide will be, just because of the size. Okay, similarly here the iodide is better than bromide, so also because of the size, but also because of the fact that it has more electrons in there, so electron density. So there is a little bit of overlap here, okay, hopefully that you can see. And that is about the strength of the nucleophile. Look at the bases also, okay? Go back to, I think it was chapter 3, acids and bases. Look at that again to figure out, what makes a good base. So once we know what kind of a nucleophile is a good one, let's talk about something else, okay, for SN1 versus SN2, because both of them don't need the same kind of nucleophile. So for example, for SN2, you cannot have a large nucleophile because you need to attack that carbon that has the leaving group, okay? So in order for that nucleophile to access that electrophilic carbon, it needs to be small. Okay, it needs to be strong and small. So that is how it works. So for example, if we look at ethoxide versus T-butoxide, T-butyl group is a larger group, right? So ethoxide, as I just drew out for you, a CH3, CH2O minus. The butoxide group will be something like this. So you have the oxide and then the T-butyl group, which is CH3, CH3, CH3. So yeah, it's going to be a better nucleophile than the ethoxide because you have more carbons in here, so more electron rich. So this is definitely stronger, but SN2 is more favored by ethoxide because this is smaller. All right, it can access that carbon. That's the more important thing. So which means that there is some ways that you can control your reactions also, okay, by changing the size of the nucleophile. Although it will give you less product, is that what you want? That's a whole other discussion. But you can drive the reaction according to the size, okay, of the nucleophile. Then the strength of the nucleophile for SN1 versus SN2. SN2 reactions need a strong nucleophile because it has to kick out the nucleophile. SN1 doesn't even care about the nucleophile as much because remember the rate determining step, or the first transition step, did not need the nucleophile at all, okay, because all it was doing in the first step was getting rid of the leaving group, creating a carbocation. So in SN1, it was not even part of the rate determining step, the nucleophile. Okay, so if it's not part of the rate determining step, you can have a weak nucleophile and get away with it. Okay, so in SN1, you can even see a lot more of the neutral nucleophiles, whereas in SN2, you will see the very traditional kind of nucleophiles. Okay, so here are some examples for you. So if you look at the strong nucleophiles, you will see that they're mostly electron rich, strong bases. Here are some moderate ones, not that great, but okay, we'll work with them. And then here are some of the weak ones, okay? Now, does it mean that because SN1 does not need a strong nucleophile, that you don't use a strong nucleophile? That's not the case, okay? That's not the answer. You can use a strong nucleophile, okay, for SN1. It doesn't need it, that's all. Okay, so we use hydroxide and iodides and all of that for SN1 reaction all the time, but you don't need it all the time. So if you can get away with something weaker, sure, use that, okay, because sometimes creating these nucleophiles, making them is also a challenge, okay, as we're going to talk about. So nucleophiles and how to make them, okay, because nucleophiles, some of them, no problem, okay, you can just get the salts and you're fine, okay. So as I said, for hydroxide, you can use sodium hydroxide. For a cyanide group or a nitrile group, you can use, potassium cyanide, that's fine. So a lot of them, you can just get the salt. Okay, that's what it's called, just the salt, and you have your nucleophile. So you can just add that to your reaction and you're done with it, okay? But in some cases, you actually have to make the nucleophile. So these nucleophiles that we are going to make here, these are called alkoxides. So I've written out the methoxide before. Here is a methoxide. So how do you make them? First of all, the nomenclature here, okay, just a little to go over this. So meth, okay, let me actually go over hydroxide first, okay. So hydroxide is this, where you have the O and the H, right? When you look at a methoxide, hydroxide, the oxide is still there, but now you have a meth, which means a 1 carbon. To have a 2 carbon would be eth, so ethoxide. Propoxide would be 3 carbons. Isopropoxide would be the isopropyl group, okay, and then comes the butyl groups and whatnot, okay. So it's simple like that, except you end with oxide. Now remember, when you have an oxide, you have to have a counter ion, okay. So the counter ion may be given to you, it may not be given to you, so don't worry about that. Now, do you have to write the counter ion for me? No, you don't, okay. You should have your nucleophile correct. You in your heart should know that there is a counter ion, okay. So if I give you a counter ion, I don't want you to freak out and say, oh, what am I going to do with the Na? Because I'm not going to write it like this. I'm going to write it like this. So you have to figure out what is the negative, what is the positive, and not worry that, oh, Na is just the counter ion, right? You can just say that and then follow on with the CH3O minus as your nucleophile. Okay, so I want you to get comfortable with that. So the nomenclature is very straightforward, just like hydroxide. You also have the alkoxides. So alk, again, the number of carbons, and then oxides, okay, O minus. Okay, so how do you actually make these alkoxides? You can make them in the lab by taking an alcohol and treating them with sodium. This is a very typical way of making it. Now you have to actually remove any kind of moisture in there, okay, and oxygen. So you have to keep it in a very insulated environment in order to make these methoxides or ethoxides, because all these alkoxides are very water sensitive, okay. So you have to be very careful. Now I want you to think about why they're water sensitive. All right, so here is an alcohol, but you can also make it with hydroxide. So alcohol with sodium hydroxide. So this is a typical acid-base reaction. Okay, so let me show you. Here is the hydroxide, here is the acidic proton, which is giving you the water, and then the rest here is the salt. So salt plus water. So very typical acid base. You can do this reaction also, but again, you have to keep removing the water, okay, from here. So I want you to think about why. First of all, you may not want to do this reaction in the lab. Second, if you do it, why do you have to remove the water? Which goes here also, as to why do you have to keep removing the water. So I want you to think about it, and then you can talk to me about if you figured out the answer, and then tell me the answer. Now let's talk about the leaving groups. The leaving groups are sort of the opposite of nucleophiles, because one clear thing was that nucleophiles are stronger bases than the leaving groups, right? So that was one clear thing we have learned already. But there are some other things in order for a leaving group to be a good leaving group. So first of all, leaving groups should be electron withdrawing groups. Okay, so when they withdraw electrons, what they do is create a polar bond to create that electrophilic carbon. Okay, because if you don't have an electrophilic carbon, then you don't have a substrate. The leaving group should be stable also once it's left. Usually, remember, the whole idea about acid-base reaction was that the reason they occur is because you're forming weaker bases and acids. So generally, when the leaving group goes, it creates a weaker base, okay, which it does. All right, and if it doesn't, then you're not going to have a reaction. Okay, so a leaving group should be stable and a weak base. Okay, so then here, of course, just tells you that, in an SN2 reaction, a weak base cannot displace a stronger one. So nucleophile has to be stronger than the leaving group. Okay, it's as simple as that. In general, halides are going to be good leaving groups. I've mentioned that before. So here is an order in which you can have the leaving groups. So tosylates, which are organic sulfonates. So remember, we have the sulfuric acid, H2SO4, Very strong acid. Very strong acid meaning HSO4 minus is a weak conjugate base. So if it's a weak conjugate base, it's an excellent leaving group. Tosylates are similar to that, okay? So look at a tosylate. This is what a sulfate would look like. And so depending on the R group, it can be different kinds of tosylates, okay? And so you can have phosphates also as very good leaving groups because they come from, they are, or I should say, they are conjugate bases of strong acids. So they make very good leaving groups, okay? So if you're thinking, how do I get them? Well, there are organic phosphates and sulfates also that we can use. We will be talking about sulfonates, this one and this one, both later on, okay? All right, so then we have the iodide, bromide, chloride. Fluoride, remember we said fluoride is not a very good nucleophile. It's not a very good leaving group either, okay? So there are some issues with fluoride. That's why nobody wants to work with fluoride. Iodide, if you remember, we said iodide was a great nucleophile because it is such a good, it's so rich in electrons, it's big in size. So iodide is a really good nucleophile, and here we are saying it's a good leaving group too. So yeah, it's a good leaving group as well, okay? So remember, Hi was a stronger acid than HBr. So if it is a stronger acid, the I minus is a strong conjugate base. So, all of these things, if you, keep in mind, yeah, there's lots to keep in mind here. So when you learn all of these things, you have to certainly, kind of use your judgment as to which reaction will be preferred. Okay, so, there are always going to be issues where, you have to kind of debate, like, what do I do here, and so then you don't look at just the one thing. You look at the substrate, you look at the nature of substrate, you look at the nucleophile and all those kind of things, and then decide, okay? So there is no memorizing in this. Here are some examples for the leaving groups, okay? And so, for example, on the top here, hydroxide, and then here's the leaving group, okay? Is this reaction going to occur? Yes, it's going to occur. So the second reaction will not happen then because hydroxide was a stronger base than Br, okay, as a base. So bromide cannot remove hydroxide, okay, as a leaving group. Now the OH is a little bit of an issue, okay, for us, because OH in organic chemistry, when it's connected like this, is an alcohol. But like this, it's a hydroxide. Okay, so please be a little bit good in your language as to what you're trying to say. Okay, this is an alcohol, but it is a hydroxide leaving group. Okay, so be careful. Anyhow, okay, so let's look at these two cases here where you have OH as the leaving group and NH2 minus. So you kind of have to identify, what the leaving group is. So here the bromide was the leaving group. Here OH minus was the leaving group. Here the leaving group is hydroxide. And then here the leaving group is OSO3H minus, okay? So in this case, they're all negatives, okay? Because they're leaving with their electrons. NH2 minus is going to be stronger than hydroxide because NH2 is coming from, where is it coming from? It's coming from ammonia, okay, which is a good base, versus hydroxide, which is coming from water. That's the conjugate base of water, hydroxide. So ammonia is a stronger base than water. Or you can say ammonia is a weaker acid than water. If it is a weaker acid, it's going to give you a stronger conjugate base, and that's how we know that this reaction is favorable, okay? OSO3H, as I just mentioned in the previous slide, is coming from H2SO4. That's the conjugate acid. H2SO4 is a strong acid, mineral acid. So this is really a weak conjugate base. So yeah, this is favorable as well. Okay. So, you kind of think like that. That's how I think. So I'm hoping that, you can kind of gather a little bit from here. Now, in this case, if you look at these two starting materials, you don't even see a leaving group, okay? Because generally when we look for a leaving group, we are looking for some heteroatom in there. And here, you know, we can see the heteroatom pretty clearly, but there is no heteroatom here. So we have to see what's going on, okay, in this case. So look at this. We have 1, 2, 3, 4 carbons, and here you have 1, 2, 3 carbons, which means a whole CH3 minus has gone, okay? We've just gotten rid of it. What happened here, in this case, OH minus, we have 1, 2, 3, 4, 1, 2, 3, 4. So in this case, the OH minus is the nucleophile, but here it replaced the hydride, okay, H minus. So the leaving groups here are coming from the carbon skeleton itself. There are no heteroatoms here. So now we have to think about whether these are going to be good leaving groups or not. To understand that, you need to look at the bases and then figure out the acids from there, okay? Because sometimes you may not know whether these are strong bases or not, but hopefully you know that CH4, which is the conjugate acid of CH3 minus, is not even considered an acid, and H minus is coming from H2. Hydrogen was never even considered as an acid. There is no acidic proton here. So which means these are really, really weak acids. If these are weak acids, these are very strong conjugate bases, which means neither of these reactions are going to happen. Okay, so take it step by step, okay, and hopefully that will help you in deciding whether reactions will take place or not. So here is a solved problem for leaving groups and whatnot. So identify the better nucleophile or leaving group in the following pair and give an explanation for your choice. So OH minus and SH minus. You're comparing them as nucleophiles, so SH minus is going to be better because it is larger in size. In these two cases here, we're looking at an oxide and an alcohol. Oxide is better because it is negatively charged. That's much better. In the case of nitrogen and then this nitrogen, both are amines, but in this nitrogen, you have more electron density, right? This one has 1 carbon. And then you have 2 hydrogens here, you have all carbon, so this one is more electron rich. Okay, so this is better. And then here, let's see, I think the second one is better because this has more carbons. Okay, so more electron rich. Solvents is the last thing, okay, that we talk about. And as I said, solvent is a little bit more of a practical thing, like when you go in the lab, how do you want to do your reaction? Because for almost all reactions you do, you need to have a solvent. What are the characteristics of a solvent? The characteristics of a solvent are that they should not react, okay, with any of the things that you have in there. And the second thing is you should be able to get rid of it. Okay, when you're ready to isolate your product, you should be able to distill it off. Okay, so which means low boiling point. You don't want something so high that you can't get rid of it. All right, so those are the characteristics. Other than that, there are 3 kinds of solvents. There is a polar protic solvent, polar aprotic, and then non-polar. Polar protic. Protic tells you there is an acidic proton in there. So if you look at all of these, they are, of course, water is considered to be an acid also. So, you know, amphoteric substance. So here you have the acidic proton, acidic proton, acidic proton, and then there are acids also. Okay, those will be all acidic protons. I'll write the acid here as well. Okay, so that would be the polar protic. The polar aprotic, they are polar solvents, but there is no acidic proton. Now remember what happens with the acidic proton. Acidic proton means that they can react with bases. So you have to be very careful, okay, with this. Polar aprotic means that you don't have any acidic proton, but they are still polar, which means that they are very good in dissolving, and they're also organic. So they're very good in dissolving organic substances. So here are a couple examples. DMF, which is dimethyl formamide. So dimethyl, and then this is the formamide part of it. And then DMSO, which is dimethyl sulfoxide. So here is the sulfoxide and then the dimethyl over here. Okay, the non-polar solvents are generally going to be low boiling points, okay, because they are non-polar, and then they are generally going to be either hydrocarbons or like diethyl ether. It's an ether functional group, okay, but they're low boiling points. So these are going to be the non-polar solvents. Now, which one do you want to use for what? So the polar protic solvents are going to be good for SN1, okay. I think I have an incomplete sentence here. I'll figure that out. But in any case, okay, the main thing here is that SN1 are going to be supported by polar protic solvents, because in this case you have a carbocation to support. All right, so polar protic is very good for this. You don't want a polar protic solvent for SN2 because otherwise the nucleophile will react with the solvent. Okay, so for apolar protic, that is SN2 kind of a reaction. All right, so which means that SN2 reactions are supported by polar aprotic solvents. Now, non-polar solvents generally, you don't use for either of them. Okay, so but they will definitely not be good for either SN2 or even SN1, because for SN1 also you need something like, something that will help stabilize the polar substances you have in there. So this is just a classification. It doesn't mean that the non-polar has to be used. Now, how will I ask you about the solvent question? Okay, so generally I ask you to classify the solvents for me. I don't ask you to memorize completely for exams as to, which solvent is going to be good for which reaction, because that's something a little bit more that you do when you get in the lab, as I said. So here is an example, okay, of what kind of a solvent you need for, the substrate, which is more like for SN1 kind of a reaction. So it is, supported a little bit by ethanol, but so much more in water. Okay, so if you have water, which is a small molecule, okay, but is protic solvent, okay, definitely protic. Ethanol is also protic, but water is more protic than ethanol and more polar than ethanol, okay. And so this SN1 is supported a lot more by water than it would be by ethanol, just to give you an example. So here are the characteristics for SN1, SN2 reactions. Okay, what kind of things you need. So for SN2, the substrate you need is primary or a methyl. For SN1, you need tertiary. So go through that, okay, because this is just a summary of what we have talked about. The last one is not something we have done yet. That's coming up in the next PowerPoint, okay, because yeah, as I said, this is a huge chapter, right? So this is only like the second part. We still have like 2 other things more to do. 3 other things to do. So lots more to do. Okay, let me just say that way. So we haven't done this part. We have done all of this, okay, so far. And then here are some problems. So here we have some starting materials. Predict the missing reagent, reactant, or product with the proper stereochemistry in the following reactions. Okay, so always write chemical structures. Do not give me the names when you're trying to do all of these problems. Okay, so make sure you draw the structures. I have to say that because some people just write the names and I don't want the name. So for you, you might want to say that, oh, I just want to give the name of this, but you don't know what name would be for this final product. Okay, because we haven't learned nomenclature yet of this compound. So I know when you are looking through the internet for your answers. Okay, so try to give me structures, don't make it obvious that you're going through Google to get your answers. Okay, but in this case, S2-bromobutane, so this is the structure for S-bromobutane. Methoxide is just methoxide. I haven't said sodium or potassium methoxide. I could easily say that also, but I just wrote methoxide. Okay, so what is the product here? The product here is going to be, this is the nucleophile kicking off the bromide. So this is the product, but then I also have to give the proper stereochemistry, which means I have to think about the mechanism. Okay, so I'm writing it as SN2. Why am I writing it as SN2? I'm writing it because this is a secondary halide. It's pretty accessible. My nucleophile is small, so it can easily access the electrophile from here. So I'm thinking it's going to be SN2 with inversion. Now, will I give you credit if you give me SN1? No. I will not, because there are some things that are pretty straightforward as being SN1 or SN2. Okay, so just because you give me inversion and then you also give me the other product and you write SN1, it doesn't mean you know the answer. It just means that you know what products you will get for SN1. That's all it means. It doesn't mean that you know whether the reaction is SN1 or SN2. I hope you get the gist, okay? So not only do you have to give me the right answer, but the mechanism should be appropriate for that substrate. Okay, so here is a product and I'm asking you to put in the substrate as well as the nucleophile. Now, generally when you look at a product like this, you look at the heteroatoms in there, and Cn is the heteroatom. So it means that Cn minus is probably going to be your nucleophile. So I wrote NaCN, but really Cn minus is the nucleophile. The substrate is going to resemble this carbon skeleton. So the only thing I need is to make sure that I have a good leaving group where the the nucleophile is. Okay, that's all. So I chose chloride. You can choose bromine also. Okay, see here it was bromine, so I can choose chloride here. Now, what kind of reaction mechanism am I expecting here? I'm expecting SN2 again, because this is a primary halide. So this was a primary carbon. So because of that, I'm thinking SN2 should work fine. So here is this molecule now, and this I've given stereochemistry again. Here is the nucleophile. If you're looking at acetone and you're wondering what the heck am I supposed to do with acetone, actually nothing, okay, because acetone is just a solvent. Generally, I try to make life easier for you. I write the solvents at the bottom of the arrow, and I write the nucleophile or the main reagent on the top of the arrow. Okay, so you kind of know that, but even otherwise, you should start recognizing solvents. So acetone is a solvent, and I know you're probably thinking, well, she hasn't taught me that acetone is a solvent. Hopefully, you're taking the lab with this lecture. Okay, so you know that acetone is a good solvent. Okay, so here is the starting material. Here is my nucleophile. This is pretty easily accessible because this is a cyclopentane. Cyclopentanes are flat molecules. Remember, they are planar rings, and so easily you can do SN2 reaction on that. So if you started with the wedge here, this will be a dash line, inverse stereochemistry. Okay. And then here we have a bromide, which is a tertiary halide. Yeah, you can see where we are going with this one. Okay, so you have iodide as the nucleophile. So in this case, this should be an SN1 reaction. Okay, now this is not the end all for all reactions. There are more videos that I have made for you. So make sure you go through those to see more reactions, because yeah, you need more examples. All right, what's going on here? Predict if the following reactions will occur or not. Now, this is an interesting thing because we've done this with acids and bases also, right? So let's talk about this. Whether a reaction is going to occur or not, what mechanism is expected, and explain your answers. Like, what are you thinking, when you answer these questions? So let's look at this one here. This is similar to what I just explained 2 slides ago, where you have the hydroxide, and then here it is attacking this carbon, so which means this is the new bond, which means that this is the carbon, this is the leaving group, right? So the leaving group is CH3 minus. Is that possible? No way, okay, because CH3 minus is coming from CH4, which is a really, really weak acid, okay? So weak acid means very strong conjugate base, so it's not a good leaving group, okay? The mechanism here that is proposed is SN2, okay, because that's a nice primary. It's not a primary, but it's a secondary leaving group, okay? So you would think, and a flat ring, so you would think it'd be an SN2 reaction. Okay, so will this reaction occur or not? This can occur, no problem, because bromide is a good nucleophile, no problem. Bromide is larger than Cl, so it's going to do, do just fine as a nucleophile. However, the product should be inverted stereochemistry, because I'm thinking that SN2 is the mechanism, because this secondary carbon is not all that crowded. Okay, so no problems. You should be able to do SN2 here. So inversion of stereochemistry is what's needed here. Okay, and what's going on here? This is fine. This is CH3O minus, so that's methoxide. Methoxide is a good enough base. That's okay. This is a tertiary halide. So if it's a tertiary halide, then the mechanism should be more like SN1. So if it is SN1, I should have more than one product in there. Okay, so all different kinds of problems I've given to you over here. So hopefully you understand what I'm expecting you to know. Okay, I think that's it in this one. And yeah, as I said, this is not it. Okay, there is so much more in SN1, SN2. So the next one will continue on because we still have to learn more exceptions.